I'm here with NASA today. We're launching the first two of a new pair of twin satellites, which together make up NASA's Tandem Reconnection and Cusp Electrodynamics Reconnaissance satellites or tracers. The spacecraft launched today at 11:13 a.m. PDT, 2:13 p.m. EDT, on a SpaceX Falcon 9 rocket from Space Launch Complex for East at Vandenberg Space Force Station in California. As part of a commercial rideshare mission with several other payloads, the spacecraft will arrive at their orbital destination after a series of orbit-raising maneuvers. Once there, the twin satellites will begin their joint mission to measure magnetic reconnection events in Earth's upper atmosphere about 3,000 times per year. So what is magnetic reconnection? How do you measure it, and why is it so important to understand? Let's dive right in. Magnetic reconnection happens when the sun's charged particles, solar wind, interact with Earth's magnetic field. Normally, the magnetic field lines funnel the solar wind around the planet like water around a dam. However, occasionally the magnetic field lines connecting the sun and Earth get stuck, causing energy to build up. When the energy reaches a critical threshold, the field lines suddenly release the stored energy and snap back on themselves, much like a rubber band snapping back to its original position. This sudden shift in the magnetic field, called magnetic reconnection, shoots a cloud of solar wind particles that would normally be diverted around our planet directly into the atmosphere at high speeds. While Earth's magnetic field protects us from the sun's superheated plasma, the impact of magnetic reconnection in the magnetosphere, the region of space dominated by Earth's magnetic field, can send shockwaves rippling into the upper layers of our atmosphere, driving atmospheric particles to very high speeds. These interactions can cause major disruptions to communications, satellites, GPS systems, and power grids on Earth. Understanding and preparing for these impacts is critical to safeguarding our modern technological infrastructure. Tracers will measure magnetic reconnection 3,000 times a year to help scientists see how quickly reconnection changes and evolves over time. This will help researchers know when they should turn their telescopes toward Earth's magnetic field to capture the best views of these events. Data from the twin satellites will be combined with observations from NASA's magnetospheric multiscale mission to better understand the formation of magnetic structures, called flux transfer events, that occur during magnetic reconnection. Flux transfer events are large-scale bursts of magnetic field that carry plasma from the sun to Earth during magnetic reconnection. As they slam into the atmosphere, they trigger global electric circuits that flow from the upper atmosphere into Earth's interior. These circuits induce electric currents that race around the globe at nearly the speed of light. While scientists understand that these events can drive electric currents around the globe, they don't yet know how reconnection and flux transfer events trigger these currents. Are they caused by a single reconnection event or many smaller ones? Do they result from a single flux transfer event or multiple ones? The tracers' data will help answer these questions. To conduct their research, each satellite carries a magnetometer, electric field detectors, and particle instruments that will work together to measure magnetic reconnection events. They will also take turns acting as a transmitter to send data about the conditions in space near the Earth's magnetic field to a orbiting relay satellite, which will forward the information to Earth. This relay satellite is provided by the rideshare mission's primary payload provider, Astrotech Space Operations, while tracers will measure magnetic reconnection near Earth's magnetic field. NASA's Punch mission, which launched in July, is measuring the structure and dynamics of the solar wind at the edge of the solar system. Punch is a 3D mapping mission utilizing a constellation of 4 small satellites that work together to observe the solar wind and its interaction with the interstellar medium. Meanwhile, NASA's ESI mission, which launched in January, is observing electrical currents flowing above the Earth's pole. Together, tracers, Punch, and ESI will help scientists understand the dynamic range of the sun's influence on the Earth's magnetosphere and atmosphere. In addition to the 3 scientific instruments on each satellite, the tracers' missions also carries 3 additional NASA-funded payloads that launched and deployed with the twin satellites. Those are the Athena EPIC SmallSat, the PEXT technology demonstration, and the Real CubeSat. The Athena EPIC, led by NASA's Langley Research Center in Hampton, Virginia, and supported by SEOPS, is designed to demonstrate an innovative, configurable way to put remote sensing instruments into orbit faster and more affordably. EPIC stands for Economical Payload Integration Cost. The Athena instrument on the satellite will test a new method for mapping the orbits of small satellites using a beacon signal, transmitted from the satellite to a network of ground stations. NASA's SCAN program, or Space Communications and Navigation, manages the PEXT technology demonstration in partnership with the Johns Hopkins Applied Physics Laboratory. That mission will showcase new technology that empowers missions to roam between communications networks in space, like cell phones roam between providers on Earth. Finally, the Real CubeSat, led by Dartmouth College in Hanover, New Hampshire, and supported by Maverick Space Systems, We'll use space as a laboratory to understand how high-energy particles within the bands of radiation that surround Earth are naturally scattered into the atmosphere. This knowledge will aid the development of methods for removing these damaging particles. 2. Better protect satellites and the critical ground systems they support. The mission is led by David Miles at the University of Iowa, with support from the Southwest Research Institute in San Antonio. NASA's Heliophysics Explorers Program Office at the agency's Goddard Space Flight Center in Greenbelt, Maryland, manages the mission for the agency's Heliophysics Division at NASA headquarters in Washington. The University of Iowa, Southwest Research Institute, University of California, Los Angeles, and University of California, Berkeley, all led instruments on tracers that will study changes in the Earth's magnetic field and electric field. NASA's Launch Services Program, based at the agency's Kennedy Space Center in Florida, manages the venture-class acquisition of dedicated and rideshare contract. The Venture-Class Launch Services VCLS contracts are managed under the auspices of the agency's Commercial Lunar Payload Services CLPS initiative. CLPS enables commercial companies to develop capabilities to deliver valuable payloads to the lunar surface cost-effectively and with greater flexibility. VCLS contracts support NASA's science, technology, engineering, education, and mathematics, or STEM, goals while fostering a robust commercial low-cost lunar economy. For more information about tracers, visit https://www.nasa.gov/mission_pages/tracers/main/index.html. For more information about heliophysics, visit https://www.nasa.gov/heliophysics. For more information about NASA's Commercial Lunar Payload Services, visit https://www.nasa.gov/launch-services/commercial-lunar-payload-services. For more information about NASA's Launch Services Program, visit https://www.nasa.gov/launch-services. For more information about NASA's Space Communications and Navigation Program, visit https://scanyouth.org. For more information about the Athena instrument, visit https://go.nasa.gov/3z9a. For more information about the PEXT instrument, visit https://go.nasa.gov/3b6n8d7. For more information about the real instrument, visit https://go.nasa.gov/3cqux9j. And thank you for watching.